Bismillahirrahmanirrahim. Assalamu alaikum. This is our 30th lecture of Formal Methods for Software Engineering, and I am Fakhr Lodi with you, discussing algebraic specifications and large family of specification languages. In the large family of specification languages, remember that we develop specifications in a two-tiered kind of approach. There are two levels of specifications written. One level of specification is written in a language which is independent of any particular implementation language, and that language is called large shared language, or LSL. Then we have the interface specifications written in the target implementation language, or written in a specification language which is closely related with the target implementation language, and that is called the large interface language. The first large interface language was the large C, and then many other more languages for writing interfaces were developed. That included C++, Modula, Java, Smalltalk, and so on and so forth. Last time we were discussing the relationship between specifications written in large shared language and then the interfaces written in the particular target language. Remember, we said that specifications written in large shared language, they form the basis of the specifications that are to be written in the interface language and then ultimately the implementation. So the algebraic specification that we write in large, they are written in LSL, and the abstract data types for which we develop the specification, that specification is called a trait, and so on and so forth. So in the interface language, what happens is that we move one step closer to actual implementation, and what we do is we move from an implementation independent syntax to a syntax which is closely related to the implementation language. We use the data types and we use the other properties of that language. For example, we now have the proper variable names, we have the proper function names, and so on and so forth. And that will form the basis for developing the final implementation. So that becomes kind of the header file for, let's say, in a C language or C++ language, and so on and so forth. Today we shall continue that discussion, and I will talk about certain properties and certain things that we need to know about the large interface languages. So let me go back onto the slide and let me read from the slide, and then I'll explain those concepts to you. At the core of each large interface language is the model of state manipulated by the associated programming language. Each specification must provide the information needed to use an interface and to write programs that implement it. So what are states? States are mapping from locks, which basically means location, and from an abstract point of view, these are abstract storage locations, also known as objects, to values. And each variable identifier has a type and is associated with a lock of that type. Now we have the concept of a state. State का जब concept आता है तो ला महला इसके साथ concept of a variable आएगा. I mean, you have to store the state at some location and some variable. So जो state का concept है, तो साथ उसके साथ location का concept भी है. So we have the notion of an abstract location. अब वो लोकेशन किस तरीके से होगी, वेरिएबल होगा, डायनेमिक वेरिएबल होगा, एरे होगी, whatever, at this point in time we are not going to talk about that, but this is where the state will be maintained, and from language to language इसका actual जो implementation है that will differ. The major kinds of values that can be stored in locks are basic values. These are mathematical constants like the integer number 3 and the letter a. Such values are independent of the state of any computation. Then we have the exposed types. These are data structures that are fully described by the type constructors of the programming language. For example, in C we have int, star, or we have array and modulo 3, array of integers, so on and so forth. And the representation is visible to and may be relied on by clients. So here we are talking about two things. There are other things that I will go back and tell you, but the first two things. पहली बात तो ये है कि we have values such as numeric values 3, 5, 10 and characters like A, B, C and so on and so forth. So these are the basic values. And then we have the types. For example, in C, we may want to have this int star, and int star actually is a pointer, but it may point to an array. So it may be the starting address of an array, and then you can manipulate this array through this pointer, as we all know. When we write programs in C, the pointers and the arrays, they are sort of interchangeable. And in some other language, for example, in modulo 3 that we had, we need to write this array, the range of the array of the type integer and so on and so forth. Now, this type that we define, that is visible to the client who is actually going to use this program or use this specification. And we are saying that, okay, now this is the interface that you are going to use, and you can rely upon that. We are not going to change it. This is what you are going to get. So this is sort of a contract or an obligation that we are making here to the client. Then we have abstract types. These types are data types that are best thought of as collections of related operations on collections of related values. These are abstract types, and they are used to hide representation information from the client. Now we have the notion of abstract data types also. Those abstract data types would be, the state would be stored in the logs. Note one thing here, that we do not have the notion of an abstract data type in a programming language like C. C में नहीं है abstract data type की notion. C++ में आपको मिल जाएगी. But from an abstract point of view, we use this abstract location that is called log in the vocabulary of large programming languages, and we use to store these objects of these abstract data types in those logs as well. Each log's type defines the kind of values it can map to in any state. Just as each log has a unique type, each LSL term has a unique sort. So we are talking about this logs. So we are associating types with this logs, and we are also associating sorts for abstract data types, the specifications written in our shared language. Now we want to connect the two tiers, and to connect the two tiers in a large specification, there is a mapping from interface language types, including abstract types to LSL sorts. Now these sorts and the types, abstract types in our interface specification, this is how we connect them together. The abstract types, they are connected to the tops, to the sorts in our shared language specifications. And then, that puts this whole thing together. यहाँ से हमने दोनों को कनेक्ट किया. तो जो आपने एब्स्ट्रैक्ट टाइप वहां पर डिफाइन की थी, यू से कि दिस एब्स्ट्रैक्ट टाइप बेसिकली इज कनेक्टेड विद दिस सॉर्ट इन दिस LSL स्पेसिफिकेशन, एंड वो यूजेस और ये वो इस तरह की चीज़ें जो हम इससे पहले देख चुके हैं, उससे हमने इसका कनेक्शन बीच में इस्टेब्लिश करना है कि कौन सी चीज़ किस चीज़ पे मैप हो रही है. ऑब्वियसली वी नीड टू प्रोवाइड अ मैपिंग सो दैट जो कंस्ट्रेंट्स नीचे हमने स्पेसिफाई किए हैं, वो कंस्ट्रेंट्स जब आप ऊपर जाते हैं, जब आप उसको इम्प्लीमेंटेशन के लेवल पे पहुंचते हैं, जब आप उसकी स्पेसिफिकेशन और फिर उसकी इम्प्लीमेंटेशन पे जाते हैं, इंटरफेस स्पेसिफिकेशन पे, तो आपको ये कैसे पता लगता है कि ये किस चीज़ के लिए ये मैंने इस पे मैप किया है, और वो जो नीचे से कंस्ट्रेंट्स जो है वो कौन सी कंस्ट्रेंट्स हैं जो मैं ऊपर लेके आऊँगा, एंड दोज कंस्ट्रेंट्स that I need to fulfill for this particular thing. This is how you make that connection or you make that join, और उसके बाद ये सारा आपका sequence बनता है. Each type of basic values, exposed types and abstract types, is based on an LSL sort. Interface specifications are written using types and values. Properties of these values are defined in LSL using operators on the corresponding sorts, and for each interface language, a standard LSL trait defines operators that can be applied to values of the sorts that the programming language's basic type and other exposed types are based upon. So here what we are saying, once again the same theme. कोई इसमें खास फर्क नहीं है, जो मैं पहले बात हम कर चुके हैं. What we are doing is, what we are saying here is कि ये जो कनेक्शन जो आपका बनेगा, आपकी जो टाइप्स इन योर इंटरफेस लैंग्वेज है, इसका कनेक्शन आपका सॉर्ट से बना. एंड रिमेंबर, जब हमने स्पेसिफिकेशन हमने लिखी थी, हमने कहा था इंट फॉर एंड, कार फॉर वैल्यू, एंड सो फोर्थ. इसका क्या मतलब था? हम ये स्पेसिफाई कर रहे हैं, हम वो कनेक्शन बीच में एस्टेब्लिश कर रहे हैं कि जो मेरा इंटरफेस लैंग्वेज में जो चीज़ मैंने टाइप डिक्लेयर की हुई है और जो मैंने एक इंडिपेंडेंट लैंग्वेज में जो टाइप डिक्लेयर की हुई है, उसका आपस में क्या कनेक्शन है. नेचुरल नंबर मेरे यहाँ पर इंटीजर की फॉर्म में आ जाते हैं. ओके, दैट इज व्हाट आई हैव इन सी. आई डोंट हैव द नोशन ऑफ अ नेचुरल नंबर इन सी. तो मुझे ये इस तरीके से लिखना होगा, ऐसे लिखना पड़ेगा. सो हर बेसिक टाइप और आपकी एब्स्ट्रैक्ट टाइप जो भी आप डिफाइन करते हैं, उसकी कॉरस्पॉन्डिंग मैपिंग हैज टू बी प्रोवाइडेड in order to make that connection and in order to provide that link so that you can use those specifications that have been written earlier on. A specification consists of a procedure header declaring the types of its arguments and results, followed by a body of the form, requires, modifies, modify list, ensures, ensure property, and so on and so forth. So when we write the procedures which corresponds to certain operations in our shared language specifications, तो वहां पर हम ये दो तीन चीजें कहते हैं. जिसे requires P, so this property is required, modifies this object or a list of objects, and ensures this properties. ये जो आपकी requires और ensures है, ये हमने शायद पहले एग्जाम्पल्स में नहीं देखी, बट ये requires और ensures जो चीज है, ये क्या चीज है? कोई आप कनेक्शन इसका बना सकते हैं? Requires is something, it says that when this function is called, so this is what is required before the function is called. And ensures mean when you return, this is what you will get. कुछ आपको याद आया? ये बिल्कुल वही चीज है जो इससे पहले हम होर्स ट्रिपल में पढ़ चुके हैं, द प्री कंडीशन एंड द पोस्ट कंडीशन, जो इससे पहले हम ऑब्जेक्ट कंस्ट्रेंट लैंग्वेज में देख चुके हैं, जो इससे पहले हम डिजाइन बाय कॉन्ट्रैक्ट में देख चुके हैं. रिक्वायर्स मीन कि इन ऑर्डर टू कॉल दिस फंक्शन और द कॉलिंग प्रोग्राम और द क्लाइंट has to ensure that this particular property is fulfilled. So it is the precondition. It is the obligation on the client. And the ensures mean this is the obligation onto this method. And then modifies means that, it will modify this particular object, which makes, which is intuitive. So once again, वो concepts जो हम इससे पहले पढ़ चुके हैं, वही कॉन्सेप्ट्स बार बार मुख्तलिफ शेप्स एंड फॉर्म्स में आपको नज़र आ रहे होंगे. सो यहाँ पर ये डिफरेंट कॉन्टेक्स्ट में हम इसको यूज़ कर रहे हैं, डिफरेंट जगह पे हम इसको यूज़ कर रहे हैं, डिफरेंट तरीके से हम इसको देख रहे हैं, बट एसेंशली वी आर यूजिंग द सेम कॉन्सेप्ट्स एंड दोज कॉन्सेप्ट्स एक्चुअली वर ओरिजिनली डेवलप्ड बाय होर एंड डाइजेक्स्ट्रा. सो उन दो हजरात की बहुत ज़बरदस्त कॉन्ट्रीब्यूशन है इस सारी की सारी फॉर्मल languages में. A specification places constraints on both clients and implementations of the procedures. The requires clause is used to state restrictions on the state, including the values of any parameters at the time of any call, and the modifies and ensures clauses place constraints on the procedure's behavior when it is called properly. They relate to states: the state when the procedure is called, the pre-state, and the state when it terminates the post-state. So here, जो हम पहले pre-condition and post-condition कहते रहे हैं, यहाँ पर वो इसको pre-state and post-state कह रहे हैं. So what is, that you start with, what is that you get at the end. बाकी exactly वही concept है, वही चीज़ है जो मैं इससे पहले बयान कर चुका हूँ. A requires clause refers only to the values in the pre-state, and an ensure clause may also refer to the values in the post-state. A modifies clause says what logs a procedure is allowed to change its target list. It says that the procedure must not change the value of any logs visible to the client except for those in the target list. Once again, जरा थोड़ी सी ये डिटेल है, बट इट इज इंट्यूटिव, नथिंग वेरी कॉम्प्लिकेटेड अबाउट इट. द रिक्वायर्स जो क्लॉज है वो आप सिर्फ इनपुट की जो आपकी वेरिएबल्स जो हैं सिर्फ उसकी फॉर्म में आप लिख सकते हैं. जो आपने इनपुट ली है, जाहिर है कि उसी पे आप कंडीशन इंपोज कर रहे हैं. आप ये कह रहे हैं कि ये रिक्वायरमेंट मस्ट बी मेट ऑन द इनपुट. सो दूसरे वेरिएबल्स जो बाद में इंट्रोड्यूस होंगे या आपके आउटपुट में इस्तेमाल हो रहे हैं, दोज वेरिएबल्स शुड नॉट कम इन द रिक्वायर्स क्लॉज. एंड एंश्योर्स ऑब्वियसली कैन यूज एनी, शुरू वाले भी, एंड वाले भी, एंड सो फोर्थ, और उसमें ओरिजिनल वैल्यूज भी और जो आखिर में आपको जो वैल्यूज मिल रही हैं वो भी. तो विद हैट एंड डैश वो दोनों तरीके से आप इसको इस्तेमाल कर सकते हैं. मॉडिफाइज provides a list of the objects or abstract locations, logs that can be modified. So the idea really is कि ये जो list जो provide की गई है, इसके अलावा बाकी जो कुछ है as input जो आया है, उसमें आप modification नहीं कर सकते. So by providing the list of the objects that can be modified, you are also sort of providing the list of the objects that cannot be modified by this particular clause, particular method. So आपका mutable and immutable जो हम इससे पहले देख चुके हैं, कि म्यूटेबल, ये जो सॉर्ट है म्यूटेबल है, इसमें ये चीज, ये वाली जो चीज़ जो है आप इसको चेंज करेंगे. एंड इम्यूटेबल, जो हमने एग्जांपल देखी थी, क्यू वाज म्यूटेबल एंड टास्क वाज इम्यूटेबल. इम्यूटेबल का मतलब ये है कि इसको आप चेंज नहीं करेंगे. तो यहाँ पर भी उससे मिलता जुलता कॉन्सेप्ट है, बट नाउ वी आर टॉकिंग अबाउट अ पर्टिकुलर मेथड, कि इस मेथड में क्या आपके पास लिस्ट ऑफ म्यूटेबल थिंग्स है. One of the advantages of large two-tiered approach to specification is that the relationship of implementation to specification is relatively straightforward. We say that if the implementation satisfies the specification, then it is a correct implementation, because the relation defined by the implementation is a subset of relations defined by the specification. Every possible behavior that can be observed by a client of the implementation is permitted by the specification. Two-tiered approach, the main purpose of the two-tiered approach was to have an easier end implementation. So एकदम से एक लंबी जंप ना हो, बल्कि there is a step in between. और वो स्टेप क्या है कि जो आपकी स्पेसिफिकेशन है उसको आप एक लेवल, यू आर टेकिंग इट टुवर्ड्स द इम्प्लीमेंटेशन. एंड वी शैल से कि जी दिस इम्प्लीमेंटेशन इज करेक्ट अगर वो जो कॉन्ट्रैक्ट जो है, जो पहले स्पेसिफिकेशंस आपने लिखी हैं, उस जो स्पेसिफिकेशन में जो कॉन्ट्रैक्ट लिखा गया है, इफ दिस इम्प्लीमेंटेशन फुलफिल्स दैट पर्टिकुलर कॉन्ट्रैक्ट. सो पॉइंट क्या है? पॉइंट ये है कि जब आप एक स्पेसिफिकेशन लिखते हैं, फॉर एग्जांपल हमने एक टेबल की केस को देखा था. टेबल में व्हाट डिड वी हैव? वी सेड वी वांटेड टू हैव एन एब्स्ट्रैक्ट डेटा टाइप टेबल इन व्हिच वी वांटेड टू कीप द इंडेक्स वैल्यू पेयर्स, द की वैल्यू पेयर्स. ये इंडेक्स है, इसके अगेंस्ट ये वैल्यू, ये इंडेक्स है, ये इसके अगेंस्ट ये वैल्यू, एंड सो एंड सो फोर्थ. एंड दोज इंडेसेस, ज़रूरी नहीं कि वो इंडेसेस 1 से लेके 100 तक हों, बीच में से गैप्स भी हो सकते हैं. एंड इन सर्टन केसेस इफ वी आर एक्चुअली टॉकिंग अबाउट एन की वैल्यू पेयर, so it could be a non-numeric thing also. But let's for the time being forget about those things. But now the question really is, did we talk about any particular implementation of that? Did we talk about any particular algorithm to get all the operations defined for that abstract data type? क्या मेरे लिए ये ज़रूरी है कि मैं इसको एरे से इम्प्लीमेंट करूं, या मैं इसको वेक्टर से करूं, या मैं इसको लिंक लिस्ट से करूं, या इसको ट्री से करूं? किस तरीके से करूं? कौन सा डेटा स्ट्रक्चर मैं यूज़ करूं? My implementation, I'm free to choose the particular implementation that I can, I want for whatever reason, efficiency या जिस तरह की जो भी बातें होंगी, as long as it fulfills all the obligations, all the constraints that have been defined in my specifications in LSL and the interface language. उन constraints को सामने रखते हुए मैं जो भी implementation करूं, वो मेरी implementation ठीक होगी. अगर वो मेरे उसका subset है, that is, it fulfills the properties that have been specified there. Let us look at one example here, and then probably that concept will be clear to you. Here is an interface specification written in LCL. So we have void choose. It takes two parameters, int x, int y, and it has this int z, and the body is, it modifies z and ensures that z dash is equal to x or z dash is equal to y. This specification, what does it say? It says that we take two values, x and y, and we return z. And what is z? Z is any one of these two values. ये या x हो सकती है या y हो सकती है। ये कौन सी होगी, वी आर नॉट स्पेसिफाइंग दैट। कम से कम ये LCL की जो स्पेसिफिकेशन लिखी हुई है इसमें नहीं है। हो सकता है इससे नीचे जो हमने शेयर्ड लैंग्वेज में स्पेसिफिकेशन लिखी थी उसमें कोई कंस्ट्रेंट हमने डिफाइन की हो, बट हियर वी डिड नॉट हैव एनी कंस्ट्रेंट। सो अगर मैं एक प्रोग्राम लिखूं विच ऑलवेज रिटर्न्स x, that program will satisfy this condition. If I write a program that always returns the second value, that is y, that would also satisfy the constraint. If I wrote a program which took a random kind of guess and returned x or y randomly, that would again satisfy. And if I wrote a program that returned the minimum of the two, once again that constraint is fulfilled. If it returned the maximum of two, I don't have a problem with that also. So there are all possible things, all possibilities. The only thing that I need to remember is that my contract must be fulfilled, and contract is that I return a value back which is either one of the two. जो मेरे दो पैरामीटर्स आए हैं उनमें से कोई एक वैल्यू वापस कर रहा हूं. So here is once again a very simple implementation, and this implementation, as I have already mentioned, कि ये as long as it returns one of the two values, it would fulfill the contract. So this implementation also does that. So this is the implementation. I have void choose int x comma int y. If x is greater than y, then z is equal to x, else z is equal to y. Now what we have here, मेरी specification जो थी वो ये कह रही थी कि जो कोई दोनों में से कोई एक वैल्यू वापस आनी चाहिए. And here I chose one particular implementation that would give me that. अब इसके पीछे कोई logic है. I need not have that logic at all there. मैं जिस तरह के मैं पहले कहा था कि अगर मैं सिर्फ जब भी आए तो मैं आपको एक x रिटर्न कर दूं, z में x वैल्यू वापस कर दूं या डाल दूं, I don't have an issue with that. But the point is, as long as the contract is fulfilled, I'm fine with that. मुझे इससे कोई issue नहीं है. So कोई भी implementation जो इस चीज को सेटिस्फाई करेगी वो ठीक होगी. अच्छा, यहां पर आप जरा इसको दोबारा दोनों को गौर से देखिए and try to see how similar the two are. The header is exactly the same. The syntax looks similar. So the idea once again was कि आपने ये प्रोसीजर की स्पेसिफिकेशन आपने लिखी है in a language which is closely related with the implementation language, और आपको ट्रांजिशन जो है towards implementation is smooth and easier. So ये इस सारी एक्सरसाइज का सारा ऑब्जेक्टिव है. So we have seen this, the basic specification in large shared language and the large interface language, and then the transition from an interface to actual implementation. Obviously, the details are there, but the basic idea I hope you would have already got. What I want to now move on to and show you is what this large prover is and how does that help us in developing specifications, and then arguing about specifications and giving us some confidence about the correctness and the completeness and consistency of those specifications. So let me now move to large prover and discuss that. LP is the large proof assistant. It is a proof assistant for a subset of multi-sorted first order logic with equality. It is designed to work efficiently on large problems and to be used by specifiers with relatively little experience with theorem proving. LP is intended primarily as an interactive proof assistant or proof debugger rather than a fully automatic theorem prover. दो तीन चीज़ें यहाँ पर नोट करने वाली हैं. First of all, this LP is based upon first order logic. So first order logic पे काम करता है, and the basic thing is that the notion of equality by putting equals for equals, जो हमारी बिल्कुल शुरू में हमने अगर आपने देखा हो, याद हो आपको, हमने इक्वलेंस पे काफ़ी डिटेल्ड लंबी चौड़ी गुफ्तगू की थी. Proofs में equivalence plays a very important role because you can substitute equals for equals and then simplify things. This large prover uses that. It is important to note that it is not really a full-fledged theorem prover. It will not be able to prove things which are complex and complicated, but it will help the developer in debugging the specifications, and I'll tell you how it does that. So ये बहुत ज़्यादा complicated किस्म की theorem proving इसमें automatic नहीं है, but it has a lot of support for developing and debugging specifications. Its design is based on the assumption that initial attempts to state and prove conjectures usually fail. So LP is designed to carry out routine but possibly lengthy proof steps automatically and to provide useful information about why proofs fail. Now here are a couple of things that need to be understood. When we write specifications, we want to argue about it, and those specifications are going to be complex. आसान नहीं है specifications को लिखना. So we incrementally develop those specifications. इसका क्या मतलब है कि किसी स्टेज पे specifications जब incremental development हो रही हैं तो they are not going to be complete. And if they are not going to be complete, you cannot really, have all the assertions validated and so on and so forth. So incomplete assertions के साथ भी ये आपका LP जो tool जो है will work and can work. So ये एक बड़ा important है. The idea really is, when you develop specifications, we all know that we make mistakes, and it is very unlikely that we will write specifications will be correct from the first time that we write it. It doesn't happen like that. So it will give you sort of where the proof fails, and then you can debug, and then you can correct the specification, and so on and so forth. To keep users from being surprised and confused by its behavior, LP does not employ complicated heuristics for finding proofs automatically. It makes it easy for user to employ standard techniques such as proof by cases, by induction, or by contradiction, but the choice among such strategies is left to the user. Now, this is a very important and interesting point here. It is not a tool that you put it there and it tells you whether the specification is correct or incorrect, proves it or disproves. What it does is that there are many different ways to prove things. You can prove things by induction, by contradiction, or by different cases, dividing it into different cases, and so on and so forth. What it does is it lets you choose the strategy and define the strategy. कि किस strategy से इसको prove करना है, and so that strategy is used to prove things, and this is a very important and interesting thing. ये हम देखेंगे अभी थोड़ी देर में कि ये कैसे इस्तेमाल हो रहा है। द लाइफ साइकिल ऑफ प्रूफ्स। प्रूविंग इज सिमिलर टू प्रोग्रामिंग. Proofs are designed, coded, debugged, and documented. Before designing a proof, it is necessary to formalize the things being reasoned about and the conjecture to be proved. Now, once again, the proofs here are actually written. So it is not kind of automatic proofs. So just like you write your program or specification or whatever, usko aap analyze karte hain, design karte hain, and then you write it and then you debug those proofs. And this is what this tool is all about, helping you in providing that kind of, support where you can do all these different things. So before you actually start, you have to do your homework. You have to know what are your conjecture and so on and so forth. So ये सारी चीज़ें आपके सामने होंगी, and then you need to come up with a proof methodology. And सिंपल केसेस के लिए शायद ये आपको ऑटोमेटिकली वो प्रूफ कर दे, लेकिन ज़्यादा कॉम्प्लिकेटेड केसेस के लिए, लाइक आई मेंशन्ड अर्लियर, ये खुद से ह्यूरिस्टिक्स यूज़ नहीं करता. यू हैव टू से कि इसको इंडक्शन से करना है, इसको इस तरीके से करना है, इसको इस तरीके से करना है, एंड देन शो कि दिस एक्चुअली हैपन्स और नॉट. Once part of proof has been coded, LP can be used to debug it. Proofs of interesting conjectures hardly ever succeed the first time. Sometimes the conjecture is wrong, sometimes the formulation is incorrect or incomplete, sometimes the proof strategy is flawed or not detailed enough. LP provides a variety of facilities that can be used to understand the problem when an attempted proof fails. While debugging proofs, users frequently reformulate axioms and conjectures. After any change in the axiomization, it is necessary to recheck not only the conjecture whose proof attempt uncovered the problem, but also the conjectures previously proved using the old axioms. LP has facilities that support such regression testing. So once again, the idea is, जिस तरीके से मैं पहले कह चुका हूँ, कि LP lets you work with incomplete proofs and lets you debug things and tells you where things fail. So when things fail, you debug and then you rewrite the conjecture and so on and so forth. और अपने आप उसको axioms और conjectures को आप ठीक करते हैं, debug करते हैं, और उसके बाद देखते हैं कि ये ठीक काम कर रहा है कि नहीं कर रहा. So then that means जिस तरीके से आप testing चल रही होती है कि when there is a defect in your program and testing highlights that and then you debug it and fix it, तो हो सकता है कि उस fix करने के नतीजे में you introduce some other bugs. जो पहले part of the code that was working now is not working anymore. That happens, and that can happen here as well in our proofs. कि आपने प्रूफ में कोई एक्सियम आपका ठीक नहीं था, उसको आपने ठीक करके दोबारा लिखा तो वो प्रॉब्लम तो दूर हो गया, लेकिन इससे पहले जो आपका प्रूफ के जो मुख्तलिफ और जो कंजेक्चर थे जो प्रूव हो रहे थे वो अब इनकरेक्ट हो गए. सो यू हैव टू सॉर्ट ऑफ नाउ रीडू द होल थिंग, सॉर्ट ऑफ डू द रिग्रेशन टेस्टिंग, एंड दिस इज द साइकिल दैट यू हैव टू फॉलो. नाउ लेट अस लुक एट a very simple trait and the corresponding proof for that. So here is a very simple trait for natural numbers. So it includes AC plus comma net, which introduces 0, which gives you a natural number. S is a function which takes a natural number and gives you a natural number, and less than, which takes two natural numbers and tells you whether the first one is less than the second one, true or false. The assertions are natural is generated by 0 and S. Those are the two constructors. For every I, J, K, which is of type nat, we say I plus 0 is equal to I, which is the identity. I plus S of J is equal to S of I plus J. So this is one theorem. This is one property that we have. I is not less than 0. So not I is less than 0. This is always true. This is a natural number. It cannot be less than 0. S of I is less than J is equal to I is less than j. So if I is less than j, then if and only if s of I is less than s of j. So these implies for every I, j, and k, which is natural, I is less than j implies I is less than j plus k. So here what we have done is we have specified the trait for natural numbers. बहुत थोड़ी सी प्रॉपर्टीज नेचुरल नंबर्स की हमने इसमें यहाँ पर लिखी हैं, कोई इसमें कॉम्प्लिकेटेड चीज़ नहीं है. बट नाउ आई विल शो यू द प्रूफ. Obviously the proof is going to be simple, but it shows a lot of things here. So the proof is once again written in LSL and or something very, very similar. And then, there is obviously a syntax associated with that, but there are certain things that are important from a proof's point of view. I will be highlighting those in a minute. So let us once again go back and look at the proof for this particular trait, and then discuss that proof. So the proof for this very simple trait is set name NAT, declare sort nat, declare variable ijk of type nat, declare operators. 0 gives us nat, s takes a nat and gives us nat, plus nat comma nat gives us nat, less than nat comma nat gives us a boolean. So this is basically corresponding to the signature part of the trait. Then we have the assert nat generated by 0 comma s, assert AC plus, assert I plus 0 is equal to I plus sj is equal to s of I plus j, not I is less than 0, 0 is less than si, si is less than sj, equal to I less than j. So the assert command supplies the LSL axioms relating the operators, and the nat generated by assertions provides an induction scheme for nat. Here is the rest of the proof. We have the set name lemma. Now we are getting into the proof. Prove I comma j implies I is less than j plus k. This was the implication that we wanted to prove. By induction on j. So we are saying do it by induction. Then we have this sort of a diamond less than greater than. Two sub goals for proof by induction on j. Basis sub goal resumes by induction on I. Then once again diamond. Two sub goals for proof by induction on I. Basis sub goal, and then induction sub goal, and then the induction sub goal for the first part of first sub goal, and then we have the conjecture, and then finally QED. As I mentioned earlier, the prove command initiates a proof by induction of the conjecture. So we have the proof and we say by induction on j. The diamond annotations are provided by LP. They indicate the introduction of sub goals of the induction. And the box, that is this empty bracket which has nothing in it, annotations are also provided by LP, and they indicate the discharge of sub goals and finally of the main proof. The resume command starts a nested induction. No other user intervention is needed to complete this proof. The QED command on the last line asks LP to confirm that there are no outstanding conjectures. So here what we have seen is once again a very simple proof. At this point in time I don't want to go into the syntactic details and so on and so forth. लेकिन दो तीन चीजें इसमें इंपॉर्टेंट हैं, दो तीन चीजें यहाँ पर हमने शो की. पहली बात तो ये थी कि there are annotations and these annotations are for LP. Two annotations हमने यहाँ पर देखी थी, एक diamond and the other one was box. And diamond annotation is sort of kind of giving us the goals and sub goals. And what we do with that is we are saying here in this particular case that, prove it by induction. So the specifier actually is specifying what kind of proof technique could be used to prove this particular property. And then we have different sub-goals, and then we have nested induction here also. कि J के लिए induction, I के लिए induction, and so on and so forth. If there are others, so that becomes उस सब गोल के अंदर induction आपने use करते हुए उसको you are going to prove it by induction. So the basis is basis, उसमें induction की जरूरत नहीं है. But the the second part requires the real induction there. And by the way, अगर आप इस particular चीज को देखेंगे तो इसको इंडक्शन के बगैर इसको प्रूव भी नहीं किया जा सकता, because you cannot have all possible states here that you can take and then show that this implication actually is fulfilled. And then we have at the end of this whole thing determination of QED, which asks this prover to check whether there were any outstanding conjectures which were not checked. और अगर इसके QED से बाहर आते हैं and there is nothing that is outstanding, that means the proof has been given and you are home. So point here is, if we have this theorem prover, not really theorem prover, the large proof debugger, if you may, it is called large prover, LP, that helps you write those proofs. जो हमने specification लिखी थी, यानी कि in that particular case the specification was intuitive, and hence the proof itself is going to be or is intuitive. But if the specifications are non-intuitive, complex specifications, so जिस तरीके से आप इसको prove आप करना चाहते हैं, the specifier tells how to prove it, because in certain cases those proofs are not going to be easy. So specifier tells that, okay, I think I can prove it by using this particular technique, and hence I write this kind of axiom, and this is what my proof will give me. So this is kind of once again a redundant axiom which basically says the same thing which the original axiom says. Okay, this is what it is supposed to do. So ये proofs जो हैं ये automatically run होंगे और फिर वो आपको बताएगा कि ये चीज prove हुई है या नहीं prove हुई. Note one thing here, कि if you cannot prove, then that does not mean it is incorrect. And on the other hand, if you show that this proof, that particular proof is there, if it does not involve all the conjectures, all the axioms, all the implications, it only wants to prove a small thing, small part, that does not show the entire thing is true. So इसका proof का scope जो है वो अपनी जगह पे limited है. इस चीज को आपको ज़हन में रखना है, इस चीज को you have to remember. So wrapping up, we have seen this large specification language, and this large specification language is a big language. There is a lot of detail of all these different things. We have obviously lots of details for our shared language. Then we have a number of interface specification languages which are there, and we can use those languages. So उसकी अपनी जगह भी detail है. Proof जो tools जो हैं वो they require a lot of attention and there is a lot of detail. we could not go into that detail. The idea here was just to show you the basic fundamentals of this large language, and I hope you have got some idea of that. इंशाल्लाह अगले लेक्चर में हम स्पेसिफिकेशंस के टॉपिक को जारी रखेंगे और कुछ और नई चीज़ों को देखेंगे. उस वक्त तक के लिए आप मुझे इजाज़त दीजिए. खुदा हाफिज़ और अस्सलाम वालेकुम.